Good morning once again, and we believe the grace of God is responsible for our life. We are picking up again, continuing from where we left in the last lecture, still on finding the root of an equation. The root of an equation. We've discussed the bisection method. That's also the same as the interval halving method. Then we look at the chord method. The chord method. That's a line joining to the curve. The chord method, which we also call the method of false position. We want to look at the Newton-Raphson's method in this particular lecture. The Newton-Raphson's method. Anytime you see names like that, which means that two people really came together and really developed something, or somebody started, another one built on it. So that's why we have a Newton-Raphson's method. Yeah, this is not so difficult. The only thing new here is this involves what we call derivative of differentiation. This use the tangent approach. So this just begin with one initial condition or one point, as compared to the interval for bisection and Newton or bisection and method of position. So we have a particular point, say x1, then we get it close to the curve, then that tangent, we have a tangent to the curve. So this curve, this line, is what the iterative procedure seeks to find. When we find this line here, this becomes the point here, then we get it close to the curve again, we get a tangent, we get a new one, we get a tangent. We keep going until we get to the exact root. Remember, this is also where the curve is crossing the x-axis. So we keep going until the interval is very small, and that point is taken as the root of the equation. So this is the tangent case. So this starts with just a particular point. As I explained in that case, you can be going to take and know that you have an interval, say a dome and a jigsaw. That is simple, but you can be going to take and just have one point. That is, you are just coming from a jigsaw, that is all. You don't know anything about a dome, and you can keep moving like that. So this is just start with just one single point. That's the initial value. We talk about initial values in partial differential equations and numerical methods and things like that. It's the same thing here. The initial value. If we draw a tangent to the curve at that, the point of intersection of the tangents to the x is taken as the next approximation to the root. This is what I was explaining graphically in the figure, the Newton-Raphson's figure below. We continue on the process until the current solution minus the previous solution is less than a given threshold value. I mentioned that graphically. I've explained that graphically. I've explained that. So this is the iterative formula. We begin with x naught. Find the functional value of x naught. Then you differentiate the function and you find that functional value of the derivative also. If we are able to do that, then that point is taken as our x1. This one doesn't need any front back substitution and things like that. That doesn't need any interval. So the x1 is used for the next iteration. You can see here. So the x1 will help us find x2. x2 will help us find x3. x3 helps us find x4. Like that going until sk helping us find sk plus 1. Like that. But when we are going and the difference between x3 minus x2 is less than epsilon, then we have to take x3 as the solution. So when assuming we get to x10 and the difference between x10 and x9 is less than epsilon, then x10 becomes our solution. What we have here is the normal mathematics. We know that the denominator can be 0. It makes the function undefined. So this can be 0 here, this can be 0 here, this can be 0, and this can be 0. This can't be 0. That is what we are trying to explain here. This is really fast. The bisection method is faster than the bisection and the force position methods. The bisection and the force position methods very faster than them all, but we may not converge to our solution if we don't start well. If we are going to take and we are starting from a GSO and you face the Accra Kumasi road, you keep moving and never get to there. That is what we are saying here, that if you face the wrong direction, you can keep going and never obtain or never have a solution So let's consider an example here. An example for this section. We solving the same problem using the Newton's method. Sometimes we just simplify it as the Newton's method without the Raphson, the Newton's method. And we are saying this is epsilon, and again our x naught is 0. Note we can take 2 also our x naught as our x naught, but the question says our x naught is 0. You can dynamize it and take s naught as 2 and still go through the procedure. You have a solution. But the other cases, it might diverge. If you take this and it diverges, you come and take this as your x naught, and definitely the solution will converge. So our x naught is the initial point we are having. So this is a general formula. So for k equal to 0, we have 1 here. We get x1, x0, 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 x0. Then we know our x0 is 0. So we need our f x naught and f prime x naught. Based on the question, this when you differentiate, we're going to get 2x plus 2. 2x plus 2. That is what we have here. 2x plus 2. Then x naught is 0. So the functional value of the derivative is 2. We have been computing this over and over. So the functional value of the x naught, that is the 0 case, is minus 3. We plug this into the formula or the iterative formula. X naught is 0, f that is minus 3, and the derivative is 2. We simplify this and we get 1.1 for x1. This one is not any interval case to compare interval as the previous cases. So we just have to check the stopping criterion at this point. But since this is the very first iteration, there is no previous value to compare with. So we move on into the next iteration. So at this point, we know that our x1 x1 is 1.5. That is what we see here. Back here, for k equal to 1, into the formula we're going to get, watch here, watch it. That's when k is equal to 1 into this becomes 2, this becomes 1, 1, 1. So that is what we have here. x2 is equal to x1 minus f over f prime, or respect to x1, x1, as we said, is 1.5. Then we put that into the derivative. We already know the derivative. Upon substitution, we're going to get 5, and this is given 2.2. We substitute here, we check that. That is 1.5 minus 2.25. That is what you see here, over 5. You simplify, and we are getting 1.05. We can check the stopping criteria at this point because we have iteration 1 and iteration 2. So solution 2 minus solution 1, this is solution x2, as we have here, 1.05, and x1, that is 1.5. So we subtract, and it's negative 0.5, but since because of the absolute value, we're going to get 0.45, and this is not less than epsilon. 0.45 is not less than 0.05. We must continue our iteration. So we know for k equal to 2, the formula reduces to that. x2 was obtained in the previous iteration. We substitute into the derivative, we have that. Then we substitute into the function itself, we have that. We put these values, this, that, and x2 itself into the formula, and we simplify as that, 1 point that. We want to check whether we have to continue the iteration or we can stop here. So the current solution is that's the x3, and the previous solution x2 is 1.05. We subtract that and we get 0.048, and this is less than epsilon. The procedure is so quick, less than epsilon, and hence we can stop the iterations. We can stop here. So we take the last x value obtained, that is x3, as the root of the equation, So we can have 1.001318 here as the root of equation. Let me go over again. We started here with the Newton-Raphson's method, which we said is a tangential technique, and as you see here, we said we start with the first tangent, we come here, second tangent, we keep going until the interval is really small. That is a stopping criterion, and we mentioned that curve or that line could be approximated with this general formula as you see here, that lines. But because we are starting with a particular value, initial value, say x0, to compute all these values, we start with 1k equal to 0 and keep going. We give ourselves an example here. We have s0 to be 0. We differentiated this to get 2x plus 2, so we put in 0 here to get the functional value, and we put it also in the derivative to get that, and we plug them back into this. We proceed, we continue in the process until the difference between two successive solutions was less than the threshold or the epsilon value, and we stop the iteration here, saying that the root of the problem is 1.0018. So this is also another example you can try your hands on. We'll end the lecture here. Stay blessed and shalom till we meet in the next session. Stay blessed.